Hi, my name is Kristen Izquierdo, and I'm currently a senior at the Bronx High School of Science. Today, I'm going to be talking about a very interesting phenomenon, otherwise known as air resistance. Let's begin with the question. What would happen if I were to drop a penny from the top of the Empire State Building? Would the pedestrian hit by the penny be killed, or simply experience a minor pain? In order to answer this question, it is important to remember Newton's second law of motion. Force is equal to mass times acceleration, and the fact that gravitational acceleration is equal to 9.8 meters per second squared. Going back to the original question, if the penny is dropped from rest and accelerates at a rate of g, then wouldn't its final velocity before it hits the pedestrian be a very large value? Although at first glance this may seem true, it is not. Why, you may ask? Well, take one good guess. Air resistance. Air resistance is defined as the frictional force exerted by air on an object in motion. It is the result of collisions between the object's surface and microscopic air molecules. To continue our discussion of air resistance, let's draw a free body diagram of the forces acting on the penny during its flight. We have the force of gravity directed downwards and air resistance directed upwards. Over time, as the velocity of the penny increases, so does the air resistance acting on it. Therefore, we can conclude that at some point throughout the penny's flight, the force of air resistance will equal the force of gravity. When this is the case, the net force will equal 0 and the penny will no longer be accelerating. The constant speed that the penny eventually reaches once air resistance prevents further acceleration is called the terminal velocity. Given that the mass of a penny is such a relatively small value, the penny will reach its terminal velocity fairly quickly. At this point, you may be asking yourself, what does this exactly mean? Well, this means that the pedestrian hit in the head by the penny will not die because both the mass and the velocity of the penny are relatively small values. All that we have discussed so far is conceptual physics. But what about math? Once again, let us draw a free body diagram for the flight of the penny. This time, the force of air resistance will be labeled kV, where k is a constant and v is the velocity. Because v is changing with respect to time, we are going to have to use a bit of calculus in order to derive a function relating v to t. The first step is to set the positive direction of the net force downward, so that F net is equal to mg minus kv. Then, we substitute Newton's law for F net, and the rest is simply pure calculus.